In this video, we're going to talk about trigonometry, particularly how it can be applied in the real world. So one of the most useful things of trigonometry is that it can help you to find the heights of things. Let's say if you want to find the height of a building. And let's say the building is over 500 feet tall. You can't really go up to the building and measure it with like a measuring tape. That's not practical. In this case, trigonometry is going to be very useful. It's going to be very helpful measuring the height of the building. What you need to know is the distance between you and the building, and you need to know the angle of elevation from the ground to the building. So let's say the angle is 30 and you're about 800 feet from the building. You can calculate the height of the building using the tangent function. Tan 30, using the rules of SOHCAHTOA, is going to equal the opposite side of the angle, which is h, divided by the adjacent side of the triangle, which is 800. So cross multiplying, you get that the height of the building is going to be 800 tan 30. And that is going to be about, so this is approximately 461.9 feet. So that's one real life application of trigonometry. It can help you to calculate the heights of large objects that you don't want to measure with a measuring tape. Now, here's another scenario. How can you measure the height of a large object if you don't know the distance between you and that object? So let me give you a situation. So let's say you're over here and there's a mountain. Now you want to measure the height of the mountain, but you're very far away. So for you to walk all the way from here to the base of the mountain, it's impractical. It's too far away to measure that. In a situation like this, how can you use trigonometry to calculate the height of that mountain if you don't know this distance? What you need to do is first measure the angle of elevation from where you are to the mountain. Let's say that angle is 20 degrees. Once you get that angle, your next step is to walk towards the mountain. Let's say after walking maybe a distance of 500 feet, you measure the new angle of elevation. You don't have to walk all the way to the mountain, just a small distance until you get a new angle. So let's say you walk 500 feet and the angle changed to 19. Now, with these two angles and the portion of distance that you walk towards the mountain, you can now find the height of that mountain. And let's go ahead and work on that example. What we need to do is break this into two triangles. This is going to be the first triangle with the 20-degree angle, and this is going to be the second triangle with the 19-degree angle. So I'm going to draw it here. So here's the first triangle. This is H, this is 20, and let's call this X1. Now for the second triangle, we have H, 19, and we'll call the distance between this point and the base of the mountain, that's going to be X2. So this is X1, this is X2. Notice that X1 is the sum of x2 and 500. So we could say that x1 is equal to x2 plus 500. So I'm going to write that here. Now let's write two equations for these two triangles. For the first one, we could say that tangent 20, think of SOHCAHTOA. TOA, tangent is opposite over adjacent. So tan 20 is going to be equal to h over x1. Now, instead of writing x1, I'm going to replace x1 with what it equals. That is x2 plus 500. Now, for the other triangle, we could say that tangent 19 is equal to the opposite side over the adjacent side. So that's h over x2. So right now we have two equations and two variables. So we can solve this. Let's put this over 1 and cross multiply. So here we have h is equal to x2 plus 500 times tan 20. Now for the other equation, we have h times 1, or h is equal to x2 tan 19. Now, because these two expressions equal h, they equal each other. So we could set them equal to each other. So we have x2 tan 19 is equal to x2 plus 500 tan 20. So now let's solve for x2. So let's distribute tan 20. We have x2 tan 19 equal, so this is going to be x2 tan 20, and then plus 500 tan 20. Now we can plug in tan 20 to get a number, but I want to save that towards the end. I'm going to move this to the other side. And then I'm going to factor out x2. Because we can get an equation directly with h, or that will directly give us h, with two angles and the distance between the two angles. So I want to get that equation first before plugging in tan 19 and tan 20. To get x2 by itself, we need to divide both sides by this. So x2 is going to be 500 tan 20 over tan 19 minus tan 20. Now that we have x2, we could plug it into this formula to get h. So h is going to be 500 tan 20, that's part of x2, and then times tan 19 over tan 19 minus tan 20. So now we can write a generic formula that will give us the height of the mountain if we know the two angles and the distance between the two angles. Let's call this d, the distance between two angles. Let's call this theta 1, the first angle we measure, and theta 2, the second angle that we measure. So the height of the mountain is going to be the distance between the two angles times tangent theta 1, and then tangent theta 2 divided by tangent theta 2 minus tangent theta 1. So this is how we can calculate the height of any object if we don't know the object or the distance between the observer and the object. All we need is two angles and the distance between the two angles. We can just plug it in directly into that formula, and that will give us the height of the unknown object. Now let's go ahead and plug this in. I do need to make one correction. I know I made this problem on the fly, but this angle here should be larger, because as you move closer to the mountain, because the horizontal distance is shorter, this angle has to be larger. So let's say this is 21 degrees as opposed to 19. So I got to make that small correction. Now let's go ahead and plug everything in. By the way, make sure this is in parentheses. So the answer is going to be approximately, it's 3511.5 feet. So that is the height of the mountain. It's about 3,500 feet. So this is the formula that you could use to calculate the height of that mountain directly. Now the next real-life application of trig is that you can calculate the distance of a faraway object, not just the height of things. So let me give you a scenario for this. Let's say you're on top of a lighthouse or something. Let's say you're right here. And let's say this is the ground, and then we have the ocean. And let's say far away on the ocean is a boat. And you want to determine how far the boat is from land. Let's say the lighthouse is like right at the edge of the cliff. So you want to calculate this distance. Now you already know the height of the lighthouse. Let's say it's 300 meters. That's how tall it is. And you measure the angle of depression to be 30 degrees. The angle of depression is the same as the angle of elevation. These two angles are alternate interior angles, and they're congruent. So with the angle of elevation, with the horizontal distance, and the height, with those three things, we can calculate the distance of the boat, how far it is away from the lighthouse. So we can use the tangent function again. It's going to be tan 30 is equal to the opposite side, that is the height, which is 300, over the adjacent side, which is d. So if we cross multiply, it's going to be 300, and that's going to equal d times tan 30. dividing both sides by tan 30, we get that the horizontal distance is going to be 300 meters over tan 30. So that's going to be approximately 519.6 meters. So that's how far the boat is away from the lighthouse. Now, you can also use trigonometry to calculate the speed of a moving object. So let's look at another situation in which we can apply that. Now, let's say if you're standing on the ground and there is a rocket that is going up. And let's say the angle of elevation at this point in time is 20 degrees. And let's say that the horizontal distance between you and the rocket, let's say it's 3,000 meters. Now, this is something that can be easily measured. You can control the distance from where you launch the rocket to where you want to measure the angle. Now, 4 seconds later, you measure a different angle. The rocket is now at a higher position. So 4 seconds later, let's say the angle, it's no longer 20, but it's much higher than that. Let's say the angle is 60 degrees. What is the average speed of the rocket during this 4-second interval? So from point A to point B, what is the average speed of the rocket during that time interval? We could use trig to calculate it. To calculate the average speed, what we need is the distance traveled divided by the total time. We have a time of 4 seconds. So what we need to do is calculate the distance between position A and position B. We just got to find that distance and divide it by 4. In this case, let's call that h. So we're looking for the vertical speed. So what we need to do is break it up into 2 triangles. For the first triangle, we have a horizontal distance of 3,000. Let's call this y1, and the angle is 20. Tan 20 is going to be y1 over 3,000. If we cross multiply, y1 is going to equal 3,000 times tan 20. So I'm just going to write that here. Now let's call this y2. So for the second triangle, this is going to be y2. The new angle is 60, and this is still 3,000. So we have tan 60 is going to be y2 over 3,000. If we cross multiply, we get that y2 is 3000 tan 60. H is the difference between y2 and y1. So the average speed between those 2 points will be h over t. H is y2 minus y1. Y2 is d times tan 60. Y1 is d times tan 20. So we can write a generic equation. Let's make the 60-degree angle theta 2 and the 20-degree angle theta 1. And let's factor out d. So this is going to be d times tangent theta 2 minus tangent theta 1 over t. So that is the generic equation that will help us to calculate the average velocity between position A and position B. All we need is the two angles, the horizontal distance between the observer and the rocket, and the time it takes to go from the first angle to the second angle. With that information, we can measure the average vertical speed of the rocket. Keep in mind, the average speed is different than the instantaneous speed. So d is 3000, and then it's going to be tan 60 minus tan 20 divided by the 4 seconds. So this is 3000 meters, and divided by 4 seconds, the average speed is going to be in meters per second. So the average speed is 1026 meters per second, approximately. What that means is that the instantaneous speed at point A is less than 1000, and the instantaneous speed at point B is going to be greater than 1000. But the average speed between points A and B is about 1000 meters per second. So that's how you can use trig to calculate the average speed of a moving object by measuring the different angles at different time periods. So if you could find how fast the angle is changing, you could find out how fast the object is moving. Now, if you want to calculate the instantaneous speed of the rocket, you need to combine trig with calculus. Let me give you an example of how you can do that. This example won't take too long. So you know the angle, the horizontal distance is constant, but the height of the rocket, that's not constant, that changes. So we're going to combine calculus with trig, which this topic is associated with something called related rates. You may want to look into that. But first, let's write an equation that relates these three letters together. So we know that tangent theta is equal to the opposite side over the adjacent side. Now I'm going to rewrite the equation as tangent theta is equal to 1 over d times h. 1 over d, this is constant. That's not going to change. We're going to take the derivative of both sides of the equation with respect to time. The derivative of tangent theta is secant squared theta, and then you need to differentiate the angle theta, which is 1, times d theta dt. 1 over d is a constant, so we're simply going to rewrite that. Now we need to differentiate h with respect to time. The derivative of h is 1 times dh dt. d theta dt, I said that wrong, d theta dt, that's the rate at which the angle is changing, which can be measured. dh dt, that's the rate at which the height is changing. That's the instantaneous speed of the rocket as it moves upward. So multiplying both sides by d, we get a formula for the instantaneous speed of the rocket. So dh dt, which we can call it Vy if we want to, that's the vertical speed of the rocket, is going to equal d times secant squared theta times d theta dt. So to calculate the instantaneous vertical speed of the rocket, we need to know the horizontal distance, which is a fixed value. We need to know the angle at that instant in time, and we need to know how fast the angle is changing with respect to time. Now secant is 1 over cosine. Secant squared is 1 over cosine squared theta. Because you don't have secant in a calculator, you have sine, cosine, and tangent. So it's better to write this formula in terms of cosine. So we can say that the vertical speed, the instantaneous vertical speed, is going to be d times d theta over dt divided by cosine squared theta. Now for this formula to work, theta has to be in radians, not in degrees. So let's say the rocket is 3,000 meters away from the observer. The angle is 30 degrees. You need to convert that to radians, so you got to multiply that by pi over 180. So that will give you an angle of pi over 6 radians. So remember, pi is equal to 180 degrees. And pi is like 3.1415 radians. Now the other thing we need is the rate at which the angle is changing. So let's say 1 second later, the angle went from 30 degrees to 35.4. Now this is a crude estimate, but you could say that the angle is changing 5.4 degrees per second. But we need that answer in radians. So to convert degrees to radians, multiply by pi, but divide by 180. So starting from 30, when you multiply by pi over 180, you get pi over 6. Doing the same thing with this value. It gives us 3 pi over 100, which is 0.09425 radians per second. So we have the horizontal distance, we have the angle in radians, and we have d theta dt in radians per second. Once you plug that in, that will give you the vertical speed of the rocket, the instantaneous vertical speed of the rocket. Now I need to clarify one little detail. D theta dt, this has to be in radians per second, because if you plug in this value, you're going to get a different result compared to if you plug in this value. So d theta dt, that has to be in radians per second. Theta, on the other hand, you can plug in degrees or you can plug in radians. Cosine 30 degrees, that's going to be the square root of 3 over 2, or 0.866. If you plug in cosine pi over 6 when your calculator is in radian mode, it will give you the same answer. So because theta is part of the cosine function, it doesn't matter if you plug it in degrees or radians. But d theta dt, that has to be in radians per second. Theta could be in radians or degrees. It will give you the same answer. But if you want to be on the safe side, you're going to be okay if you plug in all the angles in radians. So that's how you can calculate the instantaneous speed of an object. You need to know the instantaneous rate at which the angle is changing. If you have that, you can easily calculate the instantaneous speed of a moving object. Now, another application of trig is components, vector components. A vector is a quantity that has magnitude and direction. Velocity is a vector. It has magnitude and direction. Speed is not a vector. Acceleration is a vector. Force, momentum. Force could be like a physical force. It could be a magnetic force. It could be electric force. Any kind of force is a vector. Any vector can be broken up into components. And to break it into components, you need to use trig. So let's say if a person kicks a ball off the ground at a speed of 40 meters per second at an angle of 30 degrees. At the instant the ball was kicked, what is the vertical and the horizontal speed of the ball? So this represents the velocity of the ball. It's 40 meters per second, and it's at an angle of 30 degrees with the horizontal. The x component of the triangle is the horizontal speed of the ball. The y component is the vertical speed of the ball. So we need to use sine and cosine to find Vy and Vx. The hypotenuse, by the way, is 40. It's this value. So I'm just going to rewrite that here so you don't get confused by it. Sine 30, if we use SOHCAHTOA, sine is opposite over hypotenuse. Opposite to the 30-degree angle is Vy, and the hypotenuse is V, which is 40. To get V, we need to cross multiply. So Vy is equal to V times sine 30. If you follow the same process for cosine, you get that Vx is going to be V cosine 30. So this is another application of trig as it relates to physics. It allows you to find the components of any vector. It could be a velocity vector, an acceleration vector, a force vector. It could be a momentum vector. Using trig, you can find the x and y components of any vector. So if we want to finish this problem, the vertical speed of this ball is going to be 40 times sine 30. Sine 30 is a half, so half of 40 is 20. So the ball is moving upward at a vertical speed of 20 meters per second. The horizontal speed of the ball is going to be 40 cosine 30. Cosine 30 is root 3 over 2 times 40. That's going to be 20 root 3. So that's how far, or rather, how fast the ball is moving in the x direction. So that's another real-life application of trig. that is in physics. You can break down any vector into its components using sine and cosine. Now let's move on to number 5. Number 5 is very similar to number 4. We're still dealing with vectors, but tension force. So here's a common problem that you encounter in physics. Let's say you have a box, and the box is attached to 2 ropes. Let's say the box weighs 50 kilograms. I was going to say 100, but that might be too much. And let's say this is T1, T2. T is the tension force that's acting along the rope. So we have a tension force in this direction and one in this direction. Now these tension forces can be broken down into components. T1 has a horizontal component, which we'll call T1x, and it has a vertical component, which we'll call T1y. T2 also has a horizontal component, we'll call it T2x, and it has a vertical component, T2y. Now we don't know the values of T1 and T2, but what we do know is the angles they make with the horizontal. That can be measured. Let's say T1 is at an angle of 50 degrees and T2 is at an angle of 30 degrees. Now, this object has a weight force. The weight of any object is mass times gravitational acceleration. The gravitational acceleration of the Earth is 9.8 meters per second squared. So 50 times 9.8, that gives this object a weight force of 490 newtons. Now, in order to solve a problem like this, you need to use trig, because you need to break up T1 into its x and y components, and that requires sine and cosine. So to solve a problem like this, trigonometry has to be used. In order to get T1 and T2, the tension forces in the rope, you need to basically create a free body diagram, which is what we've done, and balance out all the forces in the x and y direction. In the x direction, these two forces cancel out. So we could say that T1x is equal to T2x. In the y direction, these two forces cancel out this one. T1y plus T2y is equal to 490. Now we can relate T1x and T2x in terms of T1 and T2. So this is where trig is important. T1x is going to be T1 cosine 50. T2x is going to be T2 cosine 30. So now we can relate T1 and T2. T1y is T1 sine 50. T2y is going to be T2 sine 30. And that equals 490. Now, if we divide both sides by cosine 30, we can get T2 in terms of T1. So T2 is T1 cosine 50 over cosine 30. And we can plug that in for T2 here. So now we have an equation with only T1. It's T1 sine 50 plus T1 cosine 50 over cosine 30 times sine 30, and that equals 490. So in this equation, you only have one variable, T1, which means you can now solve for T1. Once you get T1, you can plug it in here to get T2. So that's how you can solve a real-life physics problem, calculating the tension forces in the rope using trigonometry. So that's another application of trig. It helps you to solve physics problems with vectors and their components. The other application I could think of is electricity, AC circuits. AC stands for alternating current. And for this topic, there's something called phase angles that relate voltage, current, and resistance. In an AC circuit, the voltage and current, they're constantly changing. And the concept of phase angles become relevant here. I'm not going to go into too much detail into that topic. You can look it up yourself, but that's another real life application of trig, is in AC